In this video, we're going to talk about sets again. We started off the course talking a little bit about sets, but we're going to talk about sets in a little bit more detail than we have previously. And we're going to use some of our proof techniques to prove a few things about sets as well. Before we do anything new, let's do a few reminders of what we said in the first bit of the course when we talked about sets. So, what is a set? It's a collection of objects, and those objects we call elements. To say something is in a set, is an element of a set, we use this notation here. So the element A is in the set big A here. And to say it's not a member, you just use that slash through the is an element symbol. And with subsets, remember that if B is a subset of A, what does that mean? It means every element of B is also an element of A. So if A is in B, then A is in A. So remember that. We're going to use that quite a bit. In fact, we're going to use it now. Let's do this little example here. We're going to do a little proof. We're going to prove that if A is a subset of B and B is a subset of C, so that's our if part, then A is a subset of C. So let's go ahead and prove this. We'll just do a little direct proof here. And we can think of it in terms of a Venn diagram first. Sometimes this isn't a proof, but it might give you some intuition about what's going on. Well, if A is a subset of B, if A is a subset of B, if this is the set A, and if A is the subset of B, that means that everything in A is also in B. So this diagram here means A is a subset of B. You can also think of it as if A is in set A, if an element is in set A, then that element is also in set B. Or another way to phrase it, all things in set A are also in set B. And similarly, well, it says B is a subset of C. So if something is in B, then it's also in C. Or all B are C. And you can see by this diagram, hey, A is also inside C. So hopefully this gives a little intuition of what's happening here. Now let's prove this formally. So we're going to assume the if part is true. So assume that A is a subset of B, and B is a subset of C. And what we want to show is that A is a subset of C. So what we need to do is, remember, this is an if-then statement in disguise. If an element is in A, then it's also in C. So we have to show that that is true. So we'll take an element in A. So we'll call it X. Let X be some element of A. And we need to show that it's also in C. So, since A is a subset of B, remember, what's the definition of a subset? All elements of A are also in B. So, since A is an element of B, and X is an element of A, then we know that X is an element of B. That's the definition of a subset. If it's in A, then it's also in B. Okay? But we also know that B is a subset of C by assumption. That's what we assumed up here. So what does that mean? Well, we know B is a subset of C, and X is in B. Thus, x is in C. So we took an element from A, and we showed first it was in B, and then we showed, because it was in B, it's in C. Now, that's great. We just took a random element from A, showed it's in C. An arbitrary element of A is probably a better wording. Showed it's in C. There was nothing special about this element X that we picked. So, of course, this argument works for any element of set A. It's also in set C. So we've showed that A is a subset of C, and we're done. And that's how arguments with sets go. Usually, you pick an element, and you show it's in a certain set. Now, let's introduce a couple of new concepts here. Let me scroll down. We really want to know when two sets are equal. And by equal, what we mean is that they have the exact same elements. The way we show that usually is via this. We show that everything in A is in B, and we show that everything that's in B is in A. The only way for that to be true is if both sets have the exact same elements. This is the usual proof technique to show that two sets are equal. And we'll do an example of that a little bit later on. But just to know that, it's going to come back for us. I'm going to highlight it because it's very important. Two sets being equal is equivalent to each set being a subset of the other. Okay. And you can think of this notation here, this subset notation, almost like less than equals to, right? You're thinking that this set is the smaller set than the set on the right, but it could be equal to. So you're kind of thinking of this symbol like that, like a less than or equal to symbol between two numbers. But maybe you sometimes want to use just a proper subset. So you don't want it to be equal. You want it to be strictly contained, strictly smaller. And in that case, we use this symbol here without that little kind of equals bar. So it's just A is a proper subset of B. And that, of course, means A is a subset of B, but A doesn't equal B. Now, quickly, we talked about this in the first video, but remember that subset ordering of numbers that we had? So we said our smallest set that we dealt with were those natural numbers, your counting numbers. And they are, of course, contained in the whole numbers. Natural numbers start from 1, whole numbers start from 0. Now, I just wrote this proper subset symbol, but of course, if something is a proper subset, it's also a subset. So if you want to put actual subset symbols, that's fine too. Just like if one number is less than another, it's also less than or equal to. So it's the same idea, but I'll just use subset symbols. The next set we talked about were the integers. The integers, I want to use black here. The integers contain the whole numbers, so the whole numbers are a proper subset of the integers, which are a proper subset of the rational numbers. That's all your fractions, positive and negative. That is a proper subset of your real numbers. They're all the numbers that can be written as a decimal. And then finally, we talked about these complex numbers. So they're numbers that have a real part and an imaginary part. Imaginary, the part is just, we call it I, and it's the square root of -1. If you forget kind of those definitions, it's worth going back to the first video and having a look at those. Now, you could imagine us wanting to talk about elements not in a set. And if we're not careful about it, we can kind of get out of control. Imagine that we had A was the set 1, 2, 3, and I wanted to talk about elements that weren't in A. Well, 4 isn't in A, 5 isn't in A, 7 isn't in A, but you could think of things like letters. Q isn't in A, or symbols, a happy face isn't in A, or a telephone isn't in A, or Sidney Crosby isn't in A. And that's just kind of getting ridiculous, right? The only things that are in A are 1, 2, and 3. Everything else is outside of it. And that's kind of very non-useful for us. We want to be able to kind of control the objects that we're talking about a little more. And we usually do that by defining some sort of universal set. So that's all objects of the type that we're considering. And we usually denote that as U. And we'll be seeing this a little bit later when we talk about the complement of a set. And the complement is very, very similar to the idea of a negation. Now, a set that's really important to us is something called the power set. And that's just a fancy word that mathematicians use for the set of all subsets of some set A. And we usually denote it by this notation here, this curly P of A. We call that the power set. So more formally, we define it. So P of A, the power set of A, is all sets B such that there only should be one line there. I don't know why 2 got there. That should be just one line. Let's make this one line. Such that B is a subset of A. And it's kind of easier to see via a example. Once you see an example, you'll definitely see what's going on here. I'll start here with 3. So we have that C is the set 1, 2, 3. And we're interested in the power set of C. So it's all subsets. So if you remember from back in one of the first videos, the empty set is always a subset of any set. The empty set is always a subset, so we're going to include that. That is kind of this, and not even in some sense it is, the smallest subset in terms of number of elements. So the empty set is a subset. Well, let's do all the subsets that have exactly one element. So we have the subset just containing 1. You can see that this set here is a subset of C, since the set containing 1 has one element, and that element is indeed in C. So this set is a subset of C. Similarly, just containing 2 and the set just containing 3 are subsets. They're all the one element subsets. Then we have the 2 element subset. So we have 1, 2. We have 1 and 3. And we have 2 and 3. And we have the 3 element subsets. Well, there's only one, so subset. And it is everything. So it is 1, 2, and 3. So, in fact, let me make this outside bracket a little bit bigger so it looks a little clearer. So there we go. So this is the power set of C. It is all subsets of 1, 2, 3. How many do we have? We have 1, 2, 3, 4, 5, 6, 7, 8 different subsets of C. The power set is 8 elements, and those elements are subsets of C. Okay. Now let's get a little crazier. So try A and B yourselves. Think about it. It's a little tricky when you're first learning power sets, But try and figure out what the power set of A, which is just the empty set, and B, which is the set containing the empty set, think of what they are. Okay, now that you're back, well, the power set of A, well, that has nothing in it, so all that it's going to be is the empty set. There's no other subset of A, it's just the empty set. There it is. B is a little different. B is the set containing the empty set. So the power set of B, well, you always have the empty set, so we might as well put that in. But you also have any subset containing an element of the set. And so the only element of the set is the empty set. So you also have the set containing the empty set. That is another subset of B. So B has a power set that has two elements, the empty set and the set containing the empty set. And you know the empty set is always a subset of any set. And you can see here that this set here, which is just the set containing the empty set, has one element. That's the empty set. And that's an element of B, the empty set. So this set here is, of course, a subset of B. In fact, it is B. It's equal to B. And everything is a subset of itself. So this is the entire power set of B. And you can kind of see what's going on here. So what's the size of the power set of A? Well, it just has one element. The size of the power set of B is two elements. Let me make these a little bit bigger so it does indeed look like bars and not the number 1. And the size of the power set of C, as we counted, it was 8. And it can be shown always that the size of a power set, of a finite set anyway, is 2 to the number of elements in your original set. So here we had 3 elements, so the power set had, let's write it again, so this is, oh, that's not what I want to use, this is 2 to the power of 3, since there are 3 elements in A. Now the final example for this video is going to be as follows. We're going to use the idea of a power set. And this is really good because it lets us make sure we understand the definitions of a subset and a power set. We want to show that if A is a subset of B, then the power set of A is a subset of the power set of B. So we're going to do this directly. I'll start it off anyway, so I want to use black here. But anyway, we're going to do a proof. And we're going to assume that A is indeed a subset of B. So if, say, X is an element of A, then X is also an element of B. So that's what we know. And we want to show that the power set of A is a subset of the power set of B. Okay. Now, think about it. What are the elements of a power set? That's kind of the key to this. So remember, elements of the power set of a set A are subsets of A. That's the key here. So we want to show that an element of the power set of A is also an element of the power set of B. So what does that mean? It means that a subset of A is also a subset of B. So let's write that. So let's say I'm going to use a capital X since we're talking about some sort of sets. So let capital X be an element of the power set of A. Okay. Well, what does that mean? This means, and I'm going to be very explicit here by the definition of a power set. It means that X is indeed a subset of A. Okay, so stop there for a bit. See if you can continue the rest of the argument. Remember, you know that A is a subset of B, and you need to show that this set X is also in the power set of B. I'll give you one more hint. Our previous example can be very helpful to us, and so you begin to cite that to say that. So pause the video now and give that a go. Okay, so remember that I'll just do this over here. We don't need that much more room to finish this off. So also remember that from example 17.1, we have that if A is a subset of B and B is a subset of C, then A is a subset of C. So here we have X is a subset of A, and A is a subset of B. So we have this situation here. We've just proved that, so we might as well use it. So we can say by, let's say, example 17.1, since X is a subset of A and X is a subset of, A is a subset of B, then we have that X is a subset of B. We just proved that. And what did we do? We showed X was a subset of B, which means that X is an element of the power set of B. Remember, the power set has elements that are subsets. So, we've done it. We started with an element in the power set of A. We showed that that element is also in the power set of B. Thus, the power set of A is indeed a subset of the power set of B, and we're done. Power sets will come up quite a bit in this course, so make sure that you're familiar with that definition. You're comfortable using power sets and figuring them out. And these results are very powerful as well, so we'll probably see them going forward.